The tech industry's obsession with AI is beginning to hit its first physical limitation: power consumption. Training and using AI models is proving to be one of the most energy-intensive computational processes. In fact, it's estimated that a single GPT-4 textual request consumes around 30,000 watt-hours of energy, about the amount required to charge 60 iPhones. This is roughly 1,000 times more energy than what is needed for a traditional non-AI-based Google search request. One study from the Amsterdam School of Business and Economics predicts that by 2027, global AI processing will consume as much energy as Sweden, around 131 gigawatt-hours per year. When we examine the energy consumption of the human brain, it becomes clear how inefficient current AI models are. During intense mental activity, a brain consumes just 1 kilocalorie per minute, equivalent to about 17 hours of intense thought for the same energy as a basic GPT-4 request. This stark contrast has spurred a new race to develop the next generation of AI, one that more closely mimics our biology. The intense power consumption of AI is due to the underlying models of artificial neural networks. Artificial neural networks emulate biological systems to solve problems using complex statistical models. The basic structure involves interconnected nodes or neurons organized into layers. Data flows from an input layer through hidden layers to an output layer. Different architectures like convolutional neural networks for images and recurrent neural networks for time-based data are chosen based on the task. But all these networks involve massive amounts of computation, primarily through matrix multiplications and calculus. Consider the GPT-3 model developed by OpenAI. It consists of 96 layers with 12,288 neurons each, totaling 175 billion parameters. Training GPT-3 required an immense computational effort and energy consumption, highlighting the growing scale and power needs of AI models. To push past these energy limitations, researchers are exploring third-generation networks like spiking neural networks. These networks communicate through discrete spikes or pulses, mimicking biological neurons more closely and promising significant energy savings. Neuromorphic computing is another promising area, where processors are designed to physically recreate the properties of biological neurons. For example, Intel's Loihi chip features 128 clusters of 1,024 artificial neurons each, providing energy-efficient solutions for real-world problems. Despite the challenges, neuromorphic systems are advancing rapidly. The Halapoint system, featuring 1.15 billion neurons, is leading the way with incredible efficiency and speed. This hybrid approach combining digital and analog computing could revolutionize AI. As we continue to develop deeper models and more sophisticated hardware, the future of AI looks promising. The pursuit of third-generation neural networks will drive innovation, making AI more efficient and accessible than ever before.